Hello everyone. Today I'm going to be talking to you about a module called FeynmanIntegral, which is a module within the Maple physics package, which is specifically dedicated to the symbolic evaluation of Feynman integrals in Maple. This is work that I've done in collaboration with Edgardo Chapterab. So let me begin by just defining what exactly it is we're interested in evaluating. So in particle physics, the way that we're going to obtain physical predictions is that we're going to start off with an interaction Lagrangian. And from this interaction Lagrangian, we can derive Feynman rules and Feynman diagrams, which will give us something called a scattering amplitude for a specific process. So there's actually already a module in Maple called Feynman diagrams, which takes us from the interaction Lagrangian to the unintegrated amplitude. And then above leading order in the coupling constant, these amplitudes are going to have some unevaluated integrals. And what Feynman integral does is it takes this unintegrated amplitude and returns the fully integrated amplitude, which we can use to make physical predictions. So a little bit more specifically about what these integrals actually look like. These one-loop integrals, these integrals at the subleading order, say, look something like this, where we have some numerator here, f, which can be which is a polynomial basically of the loop momentum. So it can be either trivial, or it can be a scalar function of these loop momenta, or it can have some tensor indices. And these indices here represent their indices transforming under the Lorentz group. So these here are actually Lorentz four momenta, this P1. And the denominator, we have a product of Feynman propagators. So each propagator looks something like this, where you have the loop momentum plus some external momentum, capital P, all squared, minus a mass term, which represents the mass of the propagator within the diagram. And in general, these propagators can be raised to some complex number, arbitrary complex power lambda. So schematically, this number L, or rather diagrammatically, I should say, this number L represents the number of propagators that we have. So in a tadpole diagram like this, we have L equal to 1. In a bubble diagram, we have L equal to 2. The triangle has L equal to 3, box has L equal to 4, and etc. We can keep going like this. So in Maple, these Feynman integrals are going to be objects of the type Feynman integral, and we define them in this way. So we keep this definition inert for now. We have in the first argument the integrand of our integral, and in the second argument it is the loop momentum that we want to integrate over. And I'll point out that these little p's here with some subscript, this is a notation that's used for loop momenta, and capital P's are the notation that's used for external momenta. And I've highlighted them respectively in red and blue so that they're easier to see. And a second remark that I'll make is that the integral is, it can be set up in any number of dimensions that we choose, but it's going to be equal to the number of dimensions set up in the physics environment, which by default is 4, but can be changed using this setup command right here, where we input, instead of this dot dot, we put whatever dimension we're interested in computing in. Okay, and now that we have defined this bubble integral, it's very easy to actually evaluate the integral in this module. The first way that we can do this is just to activate this the Feynman integral. So doing so with this value command, we see here on the right-hand side, we have the result that we're looking for. Alternatively, we can call this evaluate command, which does the exact same thing as activating the Feynman integral. So the way that we've set up this module is to be very pedagogical. So there are several keywords that can be passed to evaluate that will allow the user to stop at any point in the computation. And basically, this will help them say if they're just trying to practice how to use or how to evaluate Feynman integrals. This is a very useful way for them to check their intermediate results. But also it can be used to generate the entire result all in one go. Okay, so let me get into the details of how this works. So yeah, as I've just mentioned, we really wanted this to be very have pedagogical applications. So we tried to follow basically in the code exactly the steps that somebody would use if they were computing these integrals using paper and pencil. So let me take you through these steps now. And with the appropriate keywords, they can stop the calculation at whichever point they want, and yeah, check intermediate results. So the first thing we want to do to perform these integrals over loop momenta is to eliminate the angular dependence of the Feynman integral. So the first step towards this is to parametrize the integral using the so-called either Feynman parametrization or the alpha or Schwinger parametrizations. And what they do, so here we have the integrand of a Feynman integral with a trivial numerator. The Feynman parameterization is going to take the denominator of this integrand and turn it into a single polynomial raised to some power lambda, which is just the sum of these complex exponents little lambda. The other parameterization scheme we can use is the alpha or Schwinger parameterization, which takes again this integrand and converts it to a sum, like a single polynomial, but in this case, the polynomial is going to be in the exponent of some exponential. So in order to perform these parametrizations, we have a dedicated function for this called parametrize. So here, without any other keywords, the default parameterization scheme used is the Feynman parameterization. But I could also go into alpha parameterization if I so choose by using this keyword parameters equals alpha. Okay, so if I just want the integrand here, so here we still have the integration signs and the integration measures, but we can get rid of these if we pass the optional argument integrand. So this parametrize is a specific function, is a specialized function for performing this parametrization, but this is also going to be the same function that's called by evaluate, and we can achieve this intermediate result by just calling evaluate with this parametrized equals true keyword. And doing so, we see we get precisely the same result as parametrize up here. And we can do, once again, the same thing with alpha parameters. The one difference that I'll note that arises when you do this using evaluate versus parametrize, notice that in parametrize, the Feynman parameters are being integrated over first, whereas in evaluate, the order of integration has been changed. And once we're actually evaluating these Feynman integrals, this is what one would typically do. They would do this parametrization, and then they would change the order of integration so that the loop momenta are integrated first. Okay, so now we have a single polynomial in the denominator here, a single polynomial of the loop momentum, but we still have some angular dependence in here. You can see that if you expand this, you're going to get little p1 dotted into capital P1, which has an angular dependence. So in order to get rid of this angular dependence, what we want to do is express this, this polynomial in terms of only p1 squared, only the loop momentum squared. And to do this, we're just going to complete the square. So I'll remind you again what we have. This is our integrand that we want to deal with. There is an internal function called shift loop momentum, which is going to do exactly this completion of the square. This has to be done through by shifting. So to eliminate the angular dependence, we have to shift the integration variable P1. And this is the shift value that we get. And this scale is just everything that's left over that is not a function of the momentum squared. So that's equivalent to this delta up here. And once again, we can obtain the shifted form directly from the function evaluate by passing the appropriate keyword. In this case, the keyword is just shifted form. So when we set this to true, we see that we get precisely the same result as we've been expecting. So what we should notice now is that the only dependence on the loop momentum inside the integrand is in this P1 squared. And since it depends only on the magnitude of the loop momentum squared, there is no more angular dependence involved. Okay, now that we've gotten rid of the angular dependence, what's left to do is to convert the integration from an integration over Minkowski space. So in this case, our metric has is in the mostly minus signature. And we can convert this to a Euclidean integration by doing what's called a Wick rotation, where we take the temporal component of the loop momentum and we just redefine it with this I and in terms of this new Euclidean momentum here, P sub E. So we are going to apply this shift into our shifted integrand. And there is an internal function that specifically does this, which is called by evaluate. But again, from the user's level, there is a keyword that will allow us to obtain precisely this level of this step of the evaluation. And in this case, the keyword is just Wick rotated. So if I set Wick rotated equal to true, then I get precisely the Wick rotated form of the integrand that I'm expecting. Okay. So now we have no more angular dependence no more dependence on the orientation of the loop momentum, and we have an integration over Euclidean space. So all that's left to do is to perform this integration. And the way this is done in practice is by converting our integral into spherical coordinates. Then we integrate over the solid angle using this formula here. And finally, we integrate over the remaining loop momentum squared. And this is done by actually performing a substitution, this kind of substitution here, which allows us to recognize the remaining integral as a beta function. So the way that we would do this using the code, we pass, if say we just want to get the result right after integrating out the loop momentum, we're going to pass this argument, loop momentum integrated equals true, to evaluate. And notice now that we've completely gotten rid of loop momentum. All that's left are these integrations over the Feynman parameters. Okay, and now to get to the final result, we still have to get rid of these Feynman parameters. And to do so, there is actually a simple formula for integrating out the Feynman parameters. The problem is that our integral does not look like this. So what I'll point out is that in order to use this formula, we must have our integrand as being simply a product of the Feynman parameters raised to some power. But as you can see from here, we actually have a polynomial of the Feynman parameters raised to some power. And to get around this, we use something called the Mellin-Barnes representation, which can be sort of thought of as a bit of the inverse of the Feynman parametrization, because what we start off with is a sum in the denominator of terms, and we convert this sum into a product of those terms, whereas the Feynman parametrization takes a product and converts it into a sum. So evaluate, the command evaluate automatically takes care of this for us. We can return the result precisely after this parameterization has been done by passing this argument MB representation equals true. And if we run this, we see that now we have in our integrand, we've introduced a new parameter, but we have a product of Feynman parameters left over. So that now we can use this formula up here. And I'll just point out one thing is that evaluate is kind of tries to do this in the most efficient way possible. So what it does is it looks for relations between the Feynman parameters, which are imposed by a delta function that already exists in the integrand. And it uses this delta function to try to reduce the integrand to the simplest form possible. So the delta function here is going to impose that the sum of xi1 and xi2 is equal to 1. And the function evaluate is just going to use this constraint to convert this trinomial into a binomial. Okay, and now that we have this simpler form where we just have products of Feynman integrals in our integrand, we can perform the integration over the Feynman parameters. And again, if we want to just stop at this step, we pass the argument Feynman parameters integrated equals true into evaluate, and this gives us the result without any Feynman parameters. And what's left for us now is that we have we've traded two parameters for one extra parameter called the Mellin-Barnes parameter, and there is an easy way to perform this integration using simply the residue theorem. There is a choice of contours that has to be made, and in our case, we've chosen the contours such that the poles of the gamma functions that are that have positive sigmas as their arguments are to the left of the contour. So we could have chosen the opposite contour, but it should give us the same result. So if we call evaluate with no keywords, what we're going to get is precisely the result after having integrated out these Mellin-Barnes parameters as well, and we obtain the final result here. Now, often it's actually going to be desirable to have a result expanded in terms of this small parameter epsilon, which is actually just a deviation from 4 dimensions. This is what you have to do if we're doing dimensional regularization. And we can obtain this expansion by passing just one more keyword to evaluate. This expand dimension equals true. So if we run this, notice that the final result is now an expansion in epsilon. So we have the leading term here is actually divergent in the limit where the space-time dimension goes to 4, which is equivalently when epsilon goes to 0. So there are a couple more sections here which will be in the supplementary material, but I will not go over them right now for the interest of time. So I've spoken to you about the simplest kinds of integrals, which are scalar integrals. So that is integrals that have no Lorentz tensor structure in the numerator. But often in calculations, we also have integrals that have a Lorentz structure in the numerator. So these integrals are what's referred to as tensor integrals. So the way that we're going to actually evaluate these tensor integrals is by first reducing them to scalar integrals, which can then be evaluated using the methods I've just shown you. So up here we have 4 classes of scalar integrals, where the numerator is just some scalar function of the loop momentum, and the denominator involves however many propagators as are relevant to your problem. And here I give an example of a tensor integral, in which case we have 2 open Lorentz indices, which are belonging to powers of the loop momentum. So the way that we're going to reduce these integrals this integral into a scalar integral is by using the so-called Passarino-Veltman reduction, which I will take you through right now. So there are 4 main steps in the Passarino-Veltman reduction, which will take a tensor integral into a basis of scalar integrals. The first of these is to express the tensor integral as a linear combination of tensor structures that could possibly appear in the final result. The next thing that we're going to do is to set up a system of equation for the coefficients of this new decomposition. And the way that we do this is by contracting this decomposition with the elements of the tensor basis themselves. Next is to express the contractions of the tensor integral in terms of scalar integrals, already at this step. And finally, we solve the system of equations for the coefficients of this decomposition in terms of the scalar integral basis. And I'm going to show you how this works for the rank 2 bubble integral, which is shown right here. So the main function for doing the tensor reduction is called tensor reduce, though the help page for that is not yet available. So the first step is to rewrite the tensor integral in terms of a basis of scalar structures that can appear in the final result. So say in this specific problem we have 1 external momentum, capital P1, and we have 2 open Lorentz indices in the numerator. So say we have this list of external momenta and this list of free Lorentz indices. We want to figure out what are the possible structures that can appear in the answer, and the answer to that is given by this command tensor basis, which when I pass to it this list of external momenta and this list of Lorentz indices gives me here a metric and this tensor structure here. So whenever there are more than 2 free Lorentz indices, we can always have a metric appearing in the final result. So the function tensor reduce is going to actually it's going to call tensor basis, and the result of using tensor basis can be isolated by passing this keyword output step equals 1. And so we see we've rewritten our tensor integral on the left-hand side in terms of a linear combination of these 2 elements of the basis. The next step is to actually set up this system of equations. And the way that we do this is by contracting this equation 25 up here with each element of the tensor basis respectively. And this is going to give us 2 equations. So we're going to have a system of 2 equations for 2 unknowns. And we isolated this step by setting output step equals to 2. The next output step simply rewrites these contractions without Lorentz indices in an unambiguous way. So let me also point out that we've done this contraction 4 minus 2 epsilon dimensions as opposed to just 4, because in the end we want to perform the integration and dimensional regularization. Now the next step is to rewrite these left-hand sides rather in terms of scalar integrals. And we're going to do this by using a formula that looks like this, which relates contractions of the loop momentum and the external momenta in terms of inverse propagators. So using output step equals to 4, we get the result of this rewriting. And now we see that on the left-hand sides, we only have scalar integrals. This can be seen because we have empty brackets over here. And we can also convert this abstract representation back into explicit integrals by using this command from abstract representation. And the final step, which we obtain by using tensor reduce with output step equals 5 or with no argument, is to simply solve the system of equations for the coefficients. So if I put output step equal to 5, I see that I have the answer right here, whereas without having plugged in the results for the coefficients C1 and C2. But if I put no optional keyword, I just get the full answer here. So on the left-hand side, I have our original tensor integral, and on the right-hand side, there's the result of the integration. So what's left over is the scalar integrals, but then we can evaluate this entire thing by just running evaluate on the output of tensor reduce. And I'll also point out that actually evaluate itself will already call tensor reduce, so you don't need to run tensor reduce first and then run evaluate. So there are some more examples here, but I will leave those for you to study if you're interested in looking at the supplementary material. Thank you.